Welcome to today's webinar. The topic today is most frequently asked questions answered by Dlubal support team. We will answer questions that our customers asked in the last time. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today, and I will do the presentation, at least the first part of the presentation. Then we'll follow the presentation from Maximilian Wittmann. He's the head of our customer support team. And of course, he knows what our customers are asking our support team. Okay, he will answer your questions when I present and vice versa. You can ask questions when you click at the button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, then let's start with the first prepared model and the first question. First question is, how can I optimize existing structures for maximum additional loads? I've prepared that hall frame, and just imagine we would like to put an additional load on the south side here. Solar panels should be placed here. And we need to check if this is possible. Let me introduce the hall frame. That beam here is an IPE 360 and the column is an IPE 450. We have different load cases, such as self-weight load case, then snow load case, 2 wind load cases, one in X direction and one in minus X direction. And there are also imperfections, this direction and the minus X direction. So the steel design was already done. Let me show you the results. We have got design ratios, 69% for the columns and then for the start of the beam here, 49.6% the design ratio. So we have a small reserve for additional loads, and let's check if we can put solar panels on the south side of this frame. So at first I switch to the self-weight load case and create an additional load for the member set. The whole beam here is a member set, and I go to insert loads, member set loads. So it should be a force, not uniform, but trapezoidal. Load direction ZL. You can see that on the image. It's okay. Then the load magnitude should be 1.2. The start is 0, and we measure the endpoint, the half beam, 10.198 meters. Okay. This member set. Okay. So let's run the steel design again. As you can see, now we have an overloading. Yeah, and we would have, or the target is to have a maximum design check ratio 1.0, and we try how much or how many solar panels can be placed here. So I go back to the self-weight load case, and in the first step I change the load, the length of the load. I start with a load length of 1 meter. Okay. And in the next step, we need to activate the add-on model optimization. So then we have to set a global parameter. I call it solar area. It's the length. Okay, solar area. That should be possible. Length, definition type, optimization. The value is currently 1 meter, and the optimization parameters are minimum 1 meter, maximum 10 meters, and the increment should be 1 meter. That's all. Leave the dialog. I go back to the load with a double click, and we assign here the formula. By clicking that button, I select the solar area. Okay, and insert. Okay. That's all for that. And the next step, I go to calculate optimization settings. Where are different optimizers, such as particle swarm, ant colony, and so on. I use all mutations. We would like to calculate all possibilities to decrease the number of calculations you can use such optimizers. Yeah, we already showed that in webinars about the add-on model optimization. Maybe Max can put in a link in the chat to that webinars. So the target value should be maximum global parameter. Yeah, the length should be optimized. Where are 10 states? I click to activate and run the optimization. So, and now all 10 possibilities, the different load combinations and the steel design is running in the background. And we get the first results. For 1 meter, we have a small reserve. Now you can see when the load length is increased, the design check ratio will also be increased. And the maximum design check ratio should be 1.0, means 100%. Okay, now we have got by 6 meters, 99.9%. And the next step should be have no overloading. Okay. Now let's calculate all optimization steps. Okay, for 10 meters, we've got an overloading over 5%. So the maximum length was the program overtook the maximum length here. And let's go to the steel design. And you can see where's the maximum design check ratio for 6 meters. That means the maximum length for the solar panels is 6 meters. You can use that on model optimization not only for loads, but also for cross sections, dimensions, and so on. Yeah, but you can see that in the webinars about model optimization add-on. Okay, that should be all for that model and for that question. It's the next model, and the next question is, can I model punching reinforcement using double-headed studs in RFEM 6? And that question was asked very often in the past, and now we can provide such a possibility. In the first step, we would like to run a punching design. So I double click at the node, and in this dialog, I check the punching design. Without only punching reinforcement in the first step, let's run the calculation. Concrete design, objects to design. Okay, we calculate the surface and that node. So then design ratio on nodes. Okay, that doesn't work. We have an overloading. And let's set or consider a punching reinforcement. I double click the node, then I select a new punching reinforcement. There are the possibility to assign vertical punching reinforcement, but also double-headed studs with a ribbed shaft or with a smooth shaft. I use the ribbed shaft, stud diameter 16 millimeters. You can choose between different distances, slabs. uniform, foundation uniform, and general. I use it for slabs. And for these parameters, for example, the number of parameters and so on, I'll leave the default setting in the first step. Okay, you can see the punching reinforcement here, and I run the calculation. So design ratio nodes. Okay, we have also an overloading. We have to put in more punching reinforcement in the slab. I double click on the punching reinforcement. So, and I have to increase, for example, the number of headed studs and so on, or the number of parameters. I change the number to 4 and run the calculation again. Okay, now it works. All design check ratios are under 1 or 1. When you double click on the line here, you can see the design check in detail. And of course, you can print these checks directly to the printer, printout report, or to a PDF. All is possible. Let's take a look at the PDF, how it would look like in the printout report. Takes some seconds. Okay. Good. That was all from my side. I hand over to Maximilian. Maximilian, it's your turn.
Yes, Andreas, thank you very much for your presentation. I will take over now and let's get started together. So a question we frequently receive in our support team concerns the load application point. So how to define the load application point, when it is critical and when it is absolutely necessary to define the load application point. So I would like to discuss this with you together using a really simple model here. So what we can see here is a single span beam with pin supports on both sides. And what is special here that I also allowed the rotation around the global z-axis so that in principle a bending around the weak axis could occur. Here on the right side we also have a sliding support so that the axial force of 1 kilonewton can act. And what is also important at that point is that this load is pretty small compared to the uniform distributed load of 10 kilonewton per meter. And this is why we would expect here a bending dominated behavior of the entire system. Okay, let's have a look into the cross-section itself. And as you can see, we have here a thin-walled open cross-section. And I think most of you are aware that here torsional buckling plays a really important role. But we will come to this point later. Let's go to the details of the cross-section. And what is also important is that we have a distance of the centroidal axis of 21.7 millimeters. And this, of course, has later an effect on the eccentricity of the external load. All right, so let's go to the base data and have a look into the add-ons. And as we can see, no add-ons have been assigned yet, but we will check here the structure stability to investigate the the torsional buckling later on. And of course, we now have to assign it to a load case. And in this case, we only have one load case, and I will activate it at that point. Okay, now the question comes up how we can define the load application point itself. And to do so, we simply can double click on the load itself. And here you find the entry eccentricity. So for your information, by default, RFEM assigns the external load to the shear center. But if we want to assign it to the center of gravity, we can check this checkbox, and you now see the load is assigned exactly here in the center of gravity, and we will expect a twisting moment at that point. Okay, let's confirm it and let's calculate everything. And in a first step, we want to have a look at the internal forces, respectively at the stress resultants. And what we can see here, of course, is we have a normal force of 1 kilonewton meter, which comes from the external load. We have a bending moment of 5 kilonewton meters. Of course, we also have the corresponding shear forces. And we also have a bending moment around the weak axis of 0.35, which results from the calculation according to second order analysis, respectively to the P delta effect. And as we expect, we also have the twisting moment here of 0.45. But what is much more interesting now is, of course, the stability analysis. Let's have a look at the critical load factor, and this is 405, which means we can increase the load by the factor of 405 until stability problems occur. And let's check the mode shapes here. And what we can observe is that we have purely lateral buckling at that point. So usually we would expect also torsional effects, but also when we check here the rotation around the x-axis, we see this is 0, which means at that point that it seems that it's only affected by the normal force. This is because we currently calculate with 6 degrees of freedom, meaning that, for example, torsion or bending moments cannot induce axial stresses, for example, here in the top flange. Okay, so in the next step, we now activate under add-ons also the torsional warping, so the calculations with 7 degrees of freedom. And calculate everything again. And now it's really interesting what happens with the factors. So if we go back to the stability analysis again, so the first thing we see is that the critical load factor dropped significantly from 405 to 9.5. So when we check the eigenmode, the mode shapes, we also can now see that the eigenmode now shows not only lateral displacement as before, but also cross-section rotations. And this is what we would expect from bending torsion or bending buckling in this case. Also, when we check the rotation around the x-axis, we now can see that this also has now an effect. And in total, this means that if we ignore torsion effects and the normal stresses resulting from them, we would significantly overestimate the entire system at that point. Yeah, but this is not even worst case scenario, because we now can additionally change the load application point to the top flange. So we then will expect additional destabilizing effects, as you know. And how can we do that? So we here can change the reference point to the most top left point, and then enter manually the distance to the center of gravity, which was 21.7. Let's hit OK. And when we now go to the side view, we see that the load straight comes down to the where the center of gravity hits the top flange. So when we now calculate everything again, we are of course once again interested in the critical load factor. And please remember, last time we had 9.5, and now it once again dropped to 7.0. And I think at this point, we really can see that as soon as we have torsional effects, it is absolutely crucial to consider the load application point and the resulting destabilizing effects. All right. Now, some RFEM expert users might say, but hey, what about our stability checks in the steel design? Aren't these effects what we have seen not covered by the stability checks? And to discuss or to explain this question, we now have a look into the steel design and go to the appropriate settings. So we find it here under steel design and then ultimate configurations. And when we double click on the default value, we have this tab here, member stability. And here you find the important section, the position of the positive transverse load application. And here the vertical position is set by default on the profile edge with the destabilizing effect. So exactly what we have seen in the previous example. However, the problem comes from the standards, because in the standards for both methods, for the equivalent member method as well as for the general method with 4 degrees of freedom, torsion is not considered in the stability checks. So as I said, once again, it comes here from the problem comes from the standards. But we really have seen how important the stability effects that result from torsion and bending are, and that they cannot be ignored at that point, especially for thin-walled open structures. And this is why for these structures where we have these torsional effects, unfortunately, the equivalent member method as well as the general method would lead to results on the unsafe side. So my answer is always, please use our add-ons with 7 degrees of freedoms to gain results on the safe side. All right. So let's move on to the second example of this webinar. We often receive the question if there is another possibility to investigate the effects of torsional warping rather than using the analysis with 7 degrees of freedom. And yes, in principle, you also could use shell elements to detect the behavior of torsional buckling. So for this, let's copy the actual system. Let's create a copy, and we copy it in a distance of 1.5 meters in the y direction, and also we include the loading here at that point. So what we have seen in the previous example is that the axial forces are of minor impact and interest here for this system, and it's dominated by the uniform distributed load. And also we can change the sliding supports to normal pin supports at that point. And what is also not necessary are here the steel design, so we can turn that one off too. Okay, so in order to create shell elements, we have a simple option here in RFEM. Just select the member, make a right click, and then under members, you can generate a surface from members. Probably you already noticed that we now lost our uniform distributed member load. This is because we are now dealing with surface elements and of course lines and line loads and not member loads anymore. What is also still remaining or still left from the original system is the centroidal axis. So we also have this information, but for now let's focus on the loading. And for this, I want to split this line to hit the center of gravity. I use the divide line command in a distance, and as I know that the center of gravity has a distance to the left side of the web from 27.1 millimeters, I additionally must subtract the half of the web thickness. So let's enter this one. It's 0.0217 minus 5 millimeters divided by 2. And here we go, we have the new point. So now we can draw the line to the other side of the beam, and we can be sure that we now are in the plane of the center of gravity. So we now can assign the line load. Still we have 10 kilonewton per meters, and we assign it to our new line. Let's hit OK. And we have our load back at that point. What still catches the eye at that point is that the pin support is connected to the centroidal line, but we do not have any connections to the surrounding surface elements up to now. But this is no problem in RFEM. We can go under types of nodes and introduce nodal links. Here in the first step, we have to select the outer nodes of the cross sections on the right and on the left side. Confirm it, and what this method does, it searches the nearest elements to these nodes. What is really important also to mention at that point is that when we think back to the member beam, we did not define any transverse stiffness, for example, in the area of the supports. So we have really a free warping behavior in the area of the supports. And we must, of course, model the same effects here for the surface elements, and for that we can release the degree of freedom in the local y direction of the rigids, which corresponds to the global x-axis. Okay, let's hit OK, and we now can see that the connection is created. And yeah, now let's have a look also in the mesh settings. And yeah, for this purpose, 0.5 meters is too coarse here, and I decide to go with 1 centimeter. And yeah, what is still missing, we now would have a free movement in the global X direction due to the introduced links. And to get a stable system, I create a new support here and introduce a really small spring at that point. Hit OK, OK, and assign it to the, it's that one here, and assign it to this node. Okay, let's check the results at that point. So it converges perfect. And in the next step, let's move on to the stability analysis and check the critical load factors. Okay, let's compare the mode shapes, and the first critical load factor can be found at 6.8, and it is assigned to the surface model here. And the next one is 7.1, which is defined, which is assigned to the member beam. So we can see we only have a deviation of approximately 4%, and this is a really good result that we achieve here. Also, I want to have a short look at the free warping at the end, and when we increase that factor a little bit, you can see that we have free warping here at the supports, and same does occur when we check the rotation around, the deformation in the X direction, and you see we have the same effect here. So one could say we have really good results also when it comes to torsional buckling and working with surface elements. All right, perfect. Okay, so let's move on to the last example. And here we want to talk about build-up cross-sections, respectively composite cross-sections. So we often receive the question how to model multiple cross-sections or assign multiple cross-sections to one line while having full control of the independent profiles. So once again, I brought a very simple model here. This is just a line with a length of 5 meters, and we have the pin supports with an axial force of 70 kilonewtons in this example. Yeah, this, for example, could be a wind bracing, and I decided to apply a compression force here in this case because I want to talk about steel design afterwards. So yeah, what would be the standard way to apply here a build-up cross-section? You see here on the left side, when you do a double click on the line, you can assign a member, and then under cross-section, we can pick a new one from the library, and you find the build-up cross-sections in this section here. So in our case, I want to use an isosceles triangle, and yeah, I think this one would be good here. But as you can see, the green line represents an interaction between both profiles, and I really want a decoupled system here. So we can go over to the second tab, and you see you can choose between different directions between the two triangles here. And the second one, you see the green line here is not there anymore, which means that we have a decoupled system in this case. So I want to go with a distance between the triangles of 20 millimeters. I hit OK. OK once again. And we now check if it is applied correctly. And yeah, this looks good. Okay, what now still catches my eye is the fact that we have to lock the rotation around the local x-axis in order to get a stable system here, because for now the beam could rotate around its own x-axis. We have to do it for both supports, also on the right side for the sliding support. Let's also activate or lock the rotation at that point. And now everything should be ready for calculation. Let's hit calculate all. And yeah, what you can see is that I already activated the steel design, but in the first step, we want to check the internal forces here. So as you can see, when we look at the normal force, you see that the axial force results in an entire normal force in the section, in the cross section, even though we have two profiles here. Of course, if you want to use, for example, this bracing in an entire system, in an entire 3D system, the stiffness is implemented correctly. So also all cross-section properties are assigned correctly. The overall behavior is correct. But if you want to perform detailed checks for every single profile, we have to find another solution. This you also can see if we go over to the steel design, we get the error that the design is not possible due to invalid section shape for design. So the question comes up how we now can achieve this point. The keyword here is line releases, but we will come to this later on. In a first step, we have to change the composite cross-section and swap it to a standard cross-section. For this, we can go to the library and you find here the standard cross-sections. We want to have an equal angle. So we can take this one, and it was a 100 times 100 times 10 millimeters. And what also catches the eye here at that point is that we have a distance to the centroidal of 28.2, but still we want to realize the gap of 20 millimeters. So we have to add additional 10 millimeters to end up in the center line. So we end up by 38.2 millimeters. All right, so we see we still have to rotate it by 90 degrees. And now we see we can assign the eccentricity to the local Z direction. This can be found under main and then eccentricities. And here we can define a new one. And for this purpose, it's good to work with absolute eccentricities, and we, as we said, in the Z direction, minus 38.2 millimeters. Let's hit OK. We have to assign it not only at the member start, but also at the member end. Let's hit OK, and let's check if everything is correct. Okay, so we have the first half of the composite cross-section at that point. Okay, now we must find a solution how we can add a second profile here and assign it to the same line. Of course, it's not the same line, but we have another possibility. And as I mentioned it, we have line releases. Let's have a look at this option. You find it here under data, and then under the special objects, we can add a new line release. So let's go through this dialog, and in the first step, we have to assign the line. Of course, it's our basic line here, and then you see, or let's have a look at the picture. What it does, it creates a second line that is released, and where we can define the interaction between the two lines. So this can be done by the line release type. Let's here create a new one, and as we don't want to have any interactions, we can check every degrees of freedom, confirm by OK. And so the next step is the released objects. In this case, I think it's clear we have to release a member. So let's select our member. And what is also very important is here the definition of objects and the nodes as definition nodes. So when we select the outer nodes at the supports, what it does, now these nodes are not copied. So these stay original, and the load transmission takes place at these points here, and we have no interaction along the lines. Okay, let's hit OK, and everything is ready here. And now we have a second line to which we can assign a second profile. Okay, perfect. This can be done by double clicking on the new line, and then we can check that the line has also a member. And when we now go to cross sections, we can choose the latest cross section here. And we can see at that point that we have to rotate it once again in the correct position. And this time we have to use 180 degrees, sorry, and this time the eccentricity must be assigned in the local y direction. So let's do this in the same way. We create a new eccentricity, once again absolute, and we assign it in the local y direction with 38.2. And once again assigned to the member start and to the member end. Let's hit OK, and hopefully now the cross section is correct. And yeah, perfect. So we see everything worked fine. But before we start the calculation, we still have to assign the effective buckling length to both profiles. We can double click on them, and then under design types, you find the effective length. We create a new one. In this case, all standard settings are okay. We want to perform all checks here, and also the nodal support settings are okay here because we have an effective length factor of 1.0. So let's confirm that and click OK. And now we are able to run the calculation. So what is our goal at this point is, of course, that the external axial force now should split up and should be assigned half of it to each profile. And this is what is happening here. So now we have the results we expect. So when we go on to the steel design, we also notice that all checks are performed, and that here flexural buckling about the principal v-axis is crucial here. And by double clicking on it, you also have the entire check on the right side. You could print that to the printout report. And yeah, so everything is as we expected. And yeah, now I'm at the end of my webinar. Andreas, thank you very much. Thanks everybody for the attention, and I'm looking forward to the next webinar. See you then. Bye bye.
Thank you, Maximilian, for your presentation. At the end of the webinar, I have additional hints for you. Hint to our online courses, for example. There's the RFEM 6 course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with RFEM 6. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. The Eurocode 8 course for the earthquake design. And the AI masterclass course for the using of the artificial intelligence. For more information and prices, just click at the links here or scan the QR codes. You can get such a course for free, at least the RFEM 6 course or Eurocode course. Just submit your project, and when we publish it on our website, then you will get such a course for free. Click at the link or scan the QR code here. There are also free online services, for example, the Dlubal community. You can ask questions there, and our support team or other community members will answer you. There's the GeoZone tool for the determination of wind, snow, and earthquake loads. You can download 3D models, for example, as a template for your project. Then you can download the free trial versions of RFEM 6, RSTAB 9, RWind 3, or R-Section. Just scan the QR code. More information can you find on our website, dlubal.com. For example, our recorded webinars, the knowledge base articles, for example. You can ask the AI assistant Mia 24/7 all the time. Just try it. Okay, it should be also all from my side. I thank you for your attention. Thanks again to Maximilian for the presentation. I wish you all a nice rest of the day. Bye-bye.